Okay, I think we can get started now. So today we're just going to review the basic model of energy, what we did last time, and we're going to go over conservation of energy. We started it last time, but it was very quickly at the end. So we're going to go over it in detail for a qualitative discussion. Then the actual quantitative discussion begins with the definition of work and some important remarks and comments on work. Then we're going to derive a formula for kinetic energy. I gave you the formula last time, but I haven't derived it, so I'm going to derive it this time. And then I forgot to write this down, but then there is activity 4. For the rest of the lecture. Okay. So do you know how I can make this stop, the screen going back and forth like this? Anyway, so last time, let's start with a review. Last time we introduced the basic model of energy. We said we have a system and we defined the system as a collection of interacting objects. This system has different kinds of energies. So we can have kinetic energy, we can have potential energy, we can have chemical energy, we can have thermal energy, ... The symbol U here I just used for potential energy in general. It could be gravitational potential energy, could be elastic potential energy, any kind of potential energy. Then the total energy of a system we denoted by the symbol E, and it's the sum of all kinds of energies. So kinetic plus gravitational potential plus spring potential plus ... All of these energies can interact and transform from one form into another. So I think I need a bigger picture for my system. So if we have kinetic energy, potential energy, chemical energy here, we denote the transformations of energy by these arrows. Like kinetic energy can be transformed into potential energy and the other way around. Chemical energy can be transformed into kinetic energy and vice versa. And then we have the environment, which is anything else that is not the system. Okay. And we said energy can be transferred to the system or out of the system by 2 processes, heat and work. So you can have energy transfer either as heat or work. Heat is a non-mechanical process by which energy is transferred from an object with high temperature to another object with low temperature. And work is a mechanical process by which energy is transferred. So by mechanical, we mean just mechanical forces, pushes and pulls, okay? We're not gonna discuss heat in this class because this requires a thermodynamic course. We're gonna focus on work, okay? But before discussing work, let's discuss conservation of energy qualitatively, and then we're gonna get to work. So conservation of energy So as we said, when work is done, energy is transferred to the system or out of the system. So we can say whenever work is done, energy is transferred, right? So this idea can be mathematically captured in this equation as the work done is equal to the change in energy. Delta means change as usual, so we can write that as W equals energy final minus energy initial. Okay. Energy initial is the sum of all energies initially in the system. Energy final is the sum of all energies finally in the system. And work done is the push or pull you do on the system to change its energy. So this is not a conservation of energy yet because energy changes here. But if we have an isolated system, which means a system that doesn't interact with its environment. So let's draw a solid boundary here. So there is no heat transfer, there is no energy transfer. Then work done is zero. There is no interaction with the environment, okay? If the net work done on the system is zero, then we call our system an isolated system. For an isolated system, if you look at the equation above, you get energy final minus energy initial equals zero, which just means energy final equal energy initial, a conservation law of energy. Energy final equals energy initial. Okay. That means no energy is transferred to the system, but it doesn't mean that energies inside the system cannot transform among each other. So explicitly, we can write the conservation law as follows. We can write that as kinetic energy final plus potential energy, gravitational potential energy final plus spring potential energy final plus ... equals kinetic energy initial plus gravitational potential energy initial plus spring potential energy initial plus ... So as long as the sum remains constant, energy or total energy is conserved. Inside the system, you can have kinetic energy transformed into potential energy as long as the total quantity is the same, okay? So transformations of energy doesn't mean we don't have energy transfer. Like energy transfer and energy transformations are not the same thing, okay? So that's it for the qualitative discussion. Now let's quantify our definition of work. So again, we need to forget about our everyday notion of the word work, which we use it to denote different things. In physics, work means a physical quantity, okay? It's usually associated with energy transfer. It's almost always associated with energy transfer, but it's not energy transfer, okay? So it's like Newton's second law when we say F equals ma. The force itself is not ma, but the force causes the acceleration. So it's a cause and effect relationship, but the force is not defined as acceleration, okay? If you want a definition of force, for example, you get a gravitational force. This is the identity of the force, or the spring force, or the electric force, or nuclear force. So, but all of these forces, their effect is to cause acceleration. This is the same thing for work and energy. When we wrote this equation down, this is not a defining equation for work, It's rather a cause and effect relation. Cause and effect relationship. The cause is work done on the system, and the effect is change in energy. Okay? But what's work itself? What is it that when it's applied changes the energy? This can be defined mathematically as follows. So let's write this as a definition. So the work done by a constant force on a system that moves for a displacement d is Fd cosine theta. Let me denote what that means in a picture. Chatra, can you get me the converter, please? Because I need to use this mouse because the screen keeps flipping. So if we have a force acting, let's say we have a box here. A pulling force is acting on the box. Okay. This is the ground. And thank you. So the box moves for a distance d, okay, from here to here, for example. So the final position of the box is here. Okay, so this is the final position. Let's denote it F. And this is the initial position. Let's denote it I. Okay. The angle between the force and displacement is theta. Okay. So this force does work on the block Fd cosine theta. Okay. F is the magnitude of the force, d is the magnitude of displacement, and cosine theta is the cosine of the angle between the force and displacement. Let me just connect the converter because the screen keeps flipping. Okay, that's better. I need to check the camera. Okay, people on Zoom, please confirm that you still can hear me.
Yep, you're good.
Okay, great. Yeah, that's much better. Okay, so this is the mathematical definition of work. This is what defines what work really is, not the equation above, because the equation above is, as we said, a cause and effect relationship. It's not work. So the left-hand side itself is Fd cosine theta, okay? Units of work. From this relationship, we see that I'm sorry for these technical issues. From the defining relationship, we see that the units of work are the same units of force times distance. So units of work are newtons times meters in SI units. And this is equivalent to joules. We give this quantity a special name, the joule. So 1 joule is 1 Newton meter. Okay. And because work is associated with any change in energy, joule is the same unit for all forms of energy. Kinetic energy is in units of joule, gravitational potential energy, chemical energy, any energy has the units of joule. Okay. And 1 joule is not a large amount of energy. It would left a small 100-gram apple, a distance of about 1 meter. So it's not a huge amount of energy. Okay, so let's take a couple of examples on this relation. Let's call this example 1. And assume that you're pulling the box horizontally. Like you don't have an angle between the force and displacement. So the force is acting like this on the block. Okay, and it moves it a distance d. So this distance is d. Let's say we have a force of 75 newtons and distance of 25 meters. So in this case, the work done is equal to FD cosine theta. In this case, theta equal to 0, so cosine 0 is 1. So this is equal to 75 newtons times 25 meters times cosine of 0 degrees. Cosine of 0 degrees is just 1. So we're left with 1,875 Newton meters, or the more standard unit is 187.5 joules. If we apply the same force over the same distance, but with an angle, let's assume we have an angle of 25 degrees. Let's assume this time theta is 25 degrees. Okay. In this case, we get the work done on the block is equal to 75 newtons times 25 meters times cosine of 25 degrees, which is equal to 1,525 or 26 joules. As you can see from these two examples, the work done when there is no angle is bigger than the work done when there is an angle, okay? Because when you're pulling the box, if you're pulling it horizontally, all the work you do is only to move it horizontally. But if you're pulling it in a different angle, only a component of your force goes into pulling the box for a horizontal amount, okay? So this is a general rule that the maximum work done is when the force in the same direction of displacement. Okay. just to get a sense of how much joules are, if we are to convert this amount of energy to kilocalories, which you find on food content, for example, you'll get, let's first write the conversion factor. We have 1 food calorie or 1 kilocalorie is equal to 4,186 joules. So if we do that conversion, we find 152.6 joules multiplied by a conversion factor, 186 joules, and above 1 kilocalorie. The units cancel out, and we're left with 0.367 kilocalories. This is nothing. Like, the average daily intake is about 2,000 calories. So this is not even 1 calorie. So if you're pulling a box with this force over 25 meters, you're doing very little work. And even though this is very small, it's typical, because even if we work all day long, we only exhaust less than 10% of the work we do goes into actual work. The rest of it goes into chemical energy that heats our body. Okay. So now let's get to some important remarks about work and how we can get important information from the defining relationship of work. But before we do that, let's just differentiate between 2 kinds of forces: external forces and internal forces. This was important already in forces in motion and Newton's 3rd law and stuff like that. And it will be important when we discuss momentum as well. So the whole discussion of systems, external versus internal, transformations versus transfers, will be important, okay? So let's write definition. External force is a force exerted by the environment on the system. It didn't show any code. Give me a second to check what happens. Chatra, what did you do when that happened?
As we're on board.
This is stupid.
Everyone.
Can you tell me what code on this?
All right.
I can't hear you. Can you raise your voice a little? No, I want you to tell me what code you see on the 3676.
But we say that it already been drawn up at the beginning.
Yeah, it's not the code anyway. Yeah, 6376. I hope this time it works. This is stupid. Again, I'm sorry for the distraction. It's technical issues. Okay, so we wanted to differentiate between two different types of forces, external forces and internal forces. External forces or external force is a force exerted by the environment on the system. And the internal force or internal forces are forces within the system. I know this seems obvious, but it's important to note because it can easily be confusing when you get it to work. Okay. So only external forces can change the energy of a system. External force does work on a system, transfers energy to the system or take energy out of the system, but internal forces only transform energies among one another within the system, but does not change the total energy of a system. Okay. So if we go back to the picture we drew for a system here, energy transfers here, we can associate with external forces, while the energy transformations happening here are associated with internal forces. Is that clear? Any questions so far? Okay. So remarks. As we said, only external forces can change the energy of a system. Internal forces cause energy transformations within the system, but don't change the energy of a system. Work is a scalar quantity. Okay, it has a magnitude, but it doesn't have a direction, which can be confusing because the next remark is that work can be positive, negative, or zero. And in kinematics, we associated positives and negatives with direction, right? But it's not general that positive and negative are directions, okay? So work can be positive, negative, or zero, but it is a scalar. So what does this positive, negative, and zero mean? Any suggestions? Any ideas? Yeah.
Whether there's anything going into or out.
Exactly, yeah. So if the work done is positive, then energy is transferred to the system. If work done is negative, then energy is transferred out of the system. And if it's zero, then there is no energy transfer at all, which we said to be conservation of energy. The third remark is that quantities F and D are positive because these are magnitudes. It's the magnitude of the force and the magnitude of displacement. So the only thing that takes care of the sign in the work definition, as we define it as FD cosine theta, is the cosine theta part. Cosine theta cares about the sign. So if you have the force, let's say we have the displacement this way and the force this way, and this is theta. Theta is less than 90 degrees, so cosine an angle less than 90 degrees is positive. So in this case, work is positive. But if it's something like this, force and distance, and this is the angle theta, then work is negative. Okay? If it's perpendicular, then there is no work done. Okay? So this is zero, this is negative, this is positive. Two important special cases are when theta equal to zero and when theta equal to 180 degrees. So when the force and displacement are in the same direction, we have theta equals 0 degrees. So cosine theta is cosine 0 degrees equal 1. Then the work done is just force times displacement. Okay, this is in one dimension. If we have the force and displacement in opposite directions, then theta equal 180 degrees, cosine theta equal cosine 180 degrees, which is -1. So the work done is negative FD. Yes. Yeah, so this takes us back to this remark. So we said it can be positive, negative, or zero, but this sign doesn't indicate direction. Rather, it indicates whether energy is transferred into the system, taken out of the system, or there is no energy transfer at all. So if energy is positive, if work is positive, then energy is transferred into the system. And if energy is negative, if work is negative, energy is taken away from the system. So it's a scalar quantity, but this sign doesn't indicate direction. Okay. If you want to think about it this way, you can think about it as the direction of energy transfer. Like energy goes from the environment to the system, meaning positive work. Okay. Does that answer your question? Okay. As we said, work can be zero, but there are 3 cases in which work can be zero. So any ideas when work can be zero? So there are three cases. Any thoughts? Let me write down the relation so you can think about it. Yeah, so this is the first case, which is the trivial case, is to have no force acting on the system at all. So nothing is happening. So work is zero. So when force is zero, no force to act on the system. Okay, what else? Distance is zero, correct. And this is actually important. If you think about pushing a wall, like imagine the same happy guy here. Pushing a wall, but he's sad because he cannot move it. Okay. So he's pushing the wall very hard, but the wall is not moving. So if we consider our system to be the wall, then there is no work done on the wall. The guy can get very tired, but no work is done. Okay. So there is a difference between being tired and doing actual work on the system. Why do you think the guy getting tired, by the way? Because this is physical, right? Something is happening.
Work being done on him.
There is work being done on him, and especially there is work being done on his muscles between the muscles, and like one muscle is pushing on the other. So there is work done inside his body, so he's getting tired. So there is work done, but not on the system of interest, which is the wall. So if D is zero, then there is no work done as well. Okay, third case. Yeah. In isolated system, work is equal to zero, yes, but this is isolated system. This is the definition of an isolated system, that there is no external forces acting on the system. But yes, that's a good point. Yeah, you look at each term in the equation and say it's zero. Okay, so cosine theta is equal to zero, which means theta is 90 degrees. As we discussed above, this just means that force and displacement are perpendicular to each other. Okay. Which can be tricky because you can drive a car, so the car is moving, but if you think of the work done by gravity on the car, it's zero, because gravity is acting vertically downwards and the car is moving horizontally, but the car is moving due to totally different forces, right? Forces from the engine, the thrust force, stuff like that. But gravity has no rule at all in moving the car, okay? So you can have work done from friction, for example, but no work done from gravity. So you have different kinds of work acting on the same system, which takes us to the notion of the net work done. So just let me just write these as A, B, and C instead of 1, 2, and 3, because I already have numbers. So number 7. I'm sorry, I had my laptop muted for some reason. Something happened. So if you were saying anything, please say it again. What was I saying? Yeah, the net work done, or the total work done, is equal to the sum of all works acting on the system. 1 + 2 + 3 + ... however many forces you have. So each force does a work, and the net work is the total work done by the forces. Okay. If the total work done is positive, then energy is transferred to the system. And if the total work done is negative, then energy is taken out of the system. If the total work done on the system is zero, then there is no energy transfer at all, as we just said. Okay, let me share with you a graph for this that summarizes. Yeah, so this graph summarizes what we discussed. It will be in the lecture notes. I just wanted you to see it in a compact way. So these are all scenarios that can happen. The first picture here is when the force in the same direction as displacement. Second picture is tilted angle, but still the force is pushing along the direction of displacement. Third case is perpendicular forces. Fourth case is force opposing the motion. And final case is just totally opposite directions, okay? With the sign of work in each one and energy transfer direction for each one, okay? That's it for work. Final thing is kinetic energy, and then I will give you the activity. So kinetic energy. We already discussed what kinetic energy is last time. We said it's energy of motion. So whenever an object is moving, it has kinetic energy by definition. But we only gave the formula for kinetic energy without proving it. So we will derive it now from all the definitions we have stated. We're gonna gather the fruits of what we did. So let's do that. Imagine our favorite example, or rather my favorite example, of a force pulling on a box for some distance delta x. Okay, so initially the block was here and finally the block is here. Okay. So in this case, theta is 0. Force and displacement are in the same direction. And imagine it's a frictionless ground, frictionless surface. The reason why I choose it to be a frictionless surface is because I want to consider only kinetic energy. I don't want any other forces to oppose the motion because I want to get a formula entirely for kinetic energy alone. So the only force acting is F, and the distance or displacement is delta x. So from the definition of work, the work done on the object will be F times delta x, right? Because cosine theta is cosine 0 in this case, which is 1. And we said there is a cause and effect relationship between work and energy, that the work done equals the change in energy, right? So this is the definition of work. This is from the definition. And this is from the cause and effect relationship, okay? We can combine both equations in one equation and say, okay, from these two equations, we have F delta x equals to delta E, right? Force times displacement equal the change of energy. In this case, the only energy changed is what? Kinetic energy, right? Is there any other form of energy that's getting changed? Yeah, nothing. Because there is no heat transfer, for example, because there is no friction. I'm only considering a block, so the chemical energy is the same, or all other forces in the block are the same. The only thing that's changing is the kinetic energy. So this change in energy, I can write down as just delta K. Okay. Okay. So let's call this equation star. Here comes our knowledge of Newton's second law and kinematics, previous chapters. So we know that F equals ma, right? So when you substitute that in equation star, we get ma delta x equals delta k, right? And then from kinematics, we have this equation, v squared equal v, or let's say v final squared equal v initial squared plus 2a delta x. Do you remember this equation? Okay. So this equation can be rearranged to get a delta x by itself. So we can put it here. Okay. So from the kinematic equation, we have a delta x equal to v final squared minus v initial squared, all divided by 2. This is just rearranging the kinematic equation. And then we can substitute that into equation double star. So we get the following: m v final squared minus v initial squared over 2 equals delta k. Which can be tidied up a little bit. Half mv final squared minus half mv initial squared equals k final minus k initial, where I wrote delta k as k final minus k initial. I just expanded what the delta means. So far, so good? Okay, so if you compare the quantities on both sides, you see that kinetic energy final corresponds to half mv final squared, and kinetic energy initial corresponds to half mv initial squared. From that, we deduce the form of kinetic energy for any velocity. So kinetic energy is half mv squared. And this is the formula that we're going to use. So as usual, I'm not going to ask you about the derivation. I'm just showing you the derivation. So when you get to a formula, you see where it came from. But the only important thing here is this formula. Okay, kinetic energy equal half mv squared. M is the mass of the object, v is the speed of the object. And as you can see, the kinetic energy doesn't depend on the direction. So if you have a block moving this way with velocity 2 meters per second, let's say it's negative 2 meters per second to the left, and another block moving with the same velocity but to the right, both of them have the same kinetic energy. Okay, this is different than momentum, which we're going to see later. Momentum is a vector, so it will be different from right to left. Yeah, that's it for today. That was the lecture part. I talked to you for an hour, so I think that's enough. Now I will give you the activity 4. I think it's not gonna take 2 hours, so whenever you finish, feel free to leave.